Hello everyone. In this video we are going to discuss about one method, call it as the false position method or regular falsy method. So before the description of the method, let us see why do we need this method. Because in the previous lectures we have seen two methods known as bisection method and secant method. So in the bisection method there is one advantage, which is that one, the root always lies between two values of the interval, that is the root bracketing we call it as. The interval always contains the root and the method converges, that is the advantage of bisection method. Whereas the disadvantage is bisection method convergence is very slow. That means we have to make lot many iterations to get closer to the exact root. So when we go to the secant method, the method converges faster compared to the bisection method, but the disadvantage is sometimes the secant method diverges also. There is no guarantee the secant method converges all the time. So secant method has one advantage, which is the faster convergence, but the disadvantage is no guarantee that it converges. So from these two methods we take the positive points. So from the bisection method we take the positive that it always converges because of the root bracketing, and in the secant method the convergence is faster because of the formula we use for the approximation. So if we combine these two positives of these two methods, bisection method and secant method, then we come up with a new method, which is false position method. So the false position method is a hybrid bisection secant method that constructs approximating lines similar to secant method but always brackets the root in the manner of bisection method. So this is how we can describe, that is we are taking the formula from the secant method to make sure the convergence is faster, but always it converges because of the bisection method root bracketing condition. That means root always lies between two values. So that checking of the root lying between two values comes from bisection method, that is root bracketing, and the formula for approximation of the root comes from the secant method. So combination of these two, secant method and bisection method, gives a hybrid bisection secant method, and we call it as false position method or sometimes we call regular falsy method. So let us see one example where the secant method diverges, because we are going for this false position method because of the disadvantage of secant method where it diverges. Let us take this example. Find an approximation to 0 of tan pi x minus x equals 0 in the interval 0, 0.48 by secant method. So the root is lying between 0 and 0.48. To apply secant method, let us start with two initial guesses. P0 is 0 and P1 is 0.48. So from these two and using the secant method formula, Pn plus 1, the next approximation, Pn minus Fpn times Pn minus 1 over Fpn minus Fpn minus 1. So if we use this formula for the secant method, we can get P2. The next approximation of the root is P1 minus, putting n equal to 1 here in place of n1. P2 is P1 minus Fp1 times P1 minus P naught over Fp1 minus Fp naught. So if we substitute P naught and P1 here in this formula, we will obtain P2 is equal to 0.181194. This is the second approximation we can say. P naught, P1, initial and first approximation Pt. This is the next approximation. Once you get P2, using P1 and P2, P1 0.48, P2 0.181194, using P1, P2, we can obtain P3 from this formula. 0.286187 is the P3. And once you get P3, from P2, P3 you can get P4. This is the next approximation. Now if you observe the errors, the first error is difference between P2 minus P1 is this value, which is of order 10 power minus 1. Next, P3 minus P2 is this error. Here, from here to here, the error is decreasing. 0.988 10 power minus 1. Here 1.0149 10 power minus 1. The error is decreasing. Next, when we go to the P4, next approximation, we are getting 1.091987, and the error is 0.8058, which is 8.058 10 power minus 1 here. So here the error is increasing, and this approximation, whatever we get, is nowhere in this interval 0.048. That means we are going away from the interval. We are going away from the exact root. Exact root lies between 0 and 0.48. But the approximation we are getting is nowhere near in this interval. Therefore, the method diverges, despite the fact that the initial interval is 0.48. So we started with the root lies between 0 and 0.48, but the approximation we are getting is nowhere in between 0 and 0.48. So the method diverges. So this is the disadvantage of secant method. Sometimes it diverges. So to come over this one, we go to the method, we call it as false position method. So let us see what is the description of false position method again. An interval an plus 1, bn plus 1 for n greater than 1, containing an approximation to the root of fx equal to 0, is found from an interval a and bn containing the root by computing this formula. So this formula is nothing but the secant method formula. After taking the secant method formula from the interval an and bn, we are getting pn. This is pn. Once you get pn, to get the next interval an plus 1, bn plus 1, we have to check this condition. If f of an times f of pn is negative, that means product of the function values at an and pn is negative, then the new interval will be an plus 1 will be an. So root lies in this part. After getting pn, if the root lies in this part, how do we check root lies in this between a and pn? This is the condition. If f of an times f of pn is negative, root lies between an and pn. Therefore, the new interval will be an plus 1 is an. So the lower limit an plus 1 for the new interval will be same as an. The upper limit bn plus 1 is equal to pn. This will be the upper limit, new upper limit, and this is the new lower limit. So an plus 1 is an and bn plus 1 is pn. If this condition is satisfied, otherwise means the root lies in this interval. Therefore, the lower limit will be, new lower limit will be pn. So an plus 1 will be pn and bn plus 1 is equal to bn. So the new upper limit is bn, the new lower limit will be Pn if this is not satisfied. So we get the formula from the secant method. After that, we check the root condition where the root lies, root bracketing condition. This root bracketing condition we take from bisection method. So this is combination of bisection method and secant method that gives false position method. So let us see in detail how does it work. So we start with the initial interval an and vn, and we get the point Pn, which is an approximation. So to get this approximation Pn, we use this secant method formula. So after getting this Pn value, now we check the root lies between these two or root lies between these two. To check the condition, we take the function values f of an, f of Pn. So product of function values at an and Pn is negative. If that happens, root lies in this interval. Therefore, the new lower limit an plus 1 will be an and bn plus 1 will be Pn. Otherwise, that means root does not lie in this. Then if the root lies in this interval, then the new lower limit will be Pn, that is an plus 1 is Pn, and new upper limit will be Bn. So Bn plus 1 will be Bn. So the new interval is an plus 1, Bn plus 1, obtained from an, Bn. That what we have written before. An plus 1, Bn plus 1 is obtained from an, Bn. So the starting interval is an, Bn. From this we get an plus 1, Bn plus 1 after finding Pn and checking this condition. So this is false position method. So previously we did one example of secant method where it diverges. Let us do the same problem by this false position method, because wherever the secant method diverges, we will follow the false position method to make sure the method converges. So if you take the same problem, find a root of the equation fx is equal to tan pi x minus 6 equals 0 in the interval 0, 0.48, accurate to at least within 10 power minus 2 by false position method. So take f of 0, the initial value 0, function value is negative. You can check by putting x is 0 here, and if we take x is 0.48, function value will be positive. So the root always lies between 0 and 0.48. So the two initial values a and bn, that is n equal to 1, a1 and b1. a1 is 0 and b1 is 0.48. From a1 and b1, we will get p1 first approximation using secant method formula. So you put a1 0, b1 0.48. If you put in this formula, you will get p1. Once you get p1, you have to check the root lies in which an and pn or pn and bn. Already we have seen f of an, f of 0, a1 is 0, f of a1 is negative, and f of b1 is positive. This is b1, so b1 is positive. Now you check function value at p1 here by putting in this function x is equal to 0.181192. So it is negative again. You can observe f of p1 is negative. So the root lies between p1 and b1, between these two, negative to positive. So the new subinterval will be, the lower limit will be p value, upper limit will be same like b1. So this p1 will be the lower limit 0.181192, upper limit will be Same B1. B1 is 0.48. The same we will take for B2. Again you find P2, the approximation from these two, A2, B2. If you put, you will get P2. Again you check the condition. So this checking condition will be like bisection method. And the formula is from secant method. That is the combination of secant method and bisection method that we will get false position method. So if we go on computing the approximations like this, we are getting error is decreasing 1.049 10 power minus 1. After that 10 power minus 2. After that 3.807 10 power minus 2. And 2.325 10 power minus 2. I think this is 10 power minus 1. We have to check this one. So the first value is 10 power minus 1. Okay. The next value this also will be 10 power minus 1, it seems. Maybe we have to check. Or so finally we are getting 2.325 10 power minus 2. That means the error is decreasing. Here you can observe the error is decreasing. 10 power minus 1, 10 power minus 2 with 6.2, 10 power minus 2 with 3.8. Next further decreasing. So the approximation of the root accurate to at least within 10 power minus 2 is 0.410305. The same problem by secant method diverges, whereas in false position method it converges. So this is how we apply the false position method. Let us see another example. Find the root of the equation fx is x square plus 10 cosine x equals 0 in the interval minus 3 minus 1. Accurate to at least within 10 power minus 2 by false position method. The same way we find function values at minus 1 and minus 3. At minus 1 it is positive, at minus 3 negative. So root lies between minus 3 and minus 1. So take a1 is minus 3, b1 is minus 1. Function value at minus 3, that is at a1, is negative. Function value at minus 1, that is at b1, is positive. So we find p1. From a1 b1 we find p1. p1 is minus 2.7535. And we find the function value at p1 by putting this p value in fx. And remember that whenever there is trigonometric function in the equation, we have to compute in radians mode, not in degrees. Always we use radians while we are doing calculations involving trigonometric functions. So if you put p value in this function, you will be getting negative again. So the root lies now between p1 and b1 because negative to positive. So the new interval where the root lies will be p1 and b1. So this p value, that is this, will be the new lower limit. Upper limit will be same like b value, previous b value. Because root lies between these two, this p value will be the new lower limit, p, and upper limit will be same like b1. So b2 will be b1, but a2 will be p1, the new p value. Again you find from a2 b2 get p3, p2. From a2 and b2 you get p2 by putting a2 b2 values in this formula. Again you find the function value at this p2. Here it turned out to be negative again, so root lies between again P2 and B2. P2 and B2. So the new interval we find by taking P value, this P value as the lower limit, upper limit will be same like previous upper limit. And we go on continuing. Here we get the root minus 1.97626, which is accurate to within 10 power minus 2, at least within 10 power minus 2. This is about the false position method. Now we'll go to another concept which is in the bisection method, how many iterations are required to obtain an accuracy of epsilon. Because in the bisection method, the method converges with a very slow rate. So the convergence is very slow in bisection method. We will see how many iterations are required to get an accuracy. So in the bisection method, we start with an interval A1 and B1. The initial values AB, we call it as A1 and B1. And suppose this is the exact root somewhere between A1 and B1, that is AB. AB, we call it as A1 and B1. That is the first interval where we start. Suppose the exact root is here. Some P is the exact root. We don't know what it is. Now the first approximation in the bisection method is P1, which is the midpoint of A1 and B1. P1 is A1 plus B1 over 2. Now once you get P1, again we get to the second interval by checking function value at P1. Suppose the root lies between A1 and P1. Then the next interval will be A2, B2, where A2 is same as A1, but B2 is same as P1. And the midpoint of A2, B2, that is P2, will be the next approximation. Like that we continue. We have seen that in bisection method. Now observe what is the error in the first approximation stage. After doing the first approximation, the error is nothing but difference between approximation and exact. That is difference between P and P1 in absolute value. Difference between P1 and P, or P and P1, either way you can say, in absolute. So the total length of this interval is B minus E. That is the total length. But already we have taken the midpoint. That means off distance is, off length is already discarded. This we are discarding. We are taking only this because P1 is the midpoint. Now the root will be P1. P is the root, and the difference between the exact root and the approximation cannot be more than half of this total length. The total length of this interval is B minus A. Because we have taken the midpoint as P1, so that is the half of the length is discarded. We are not considering this off distance because P1 is the midpoint. Therefore, the difference between exact and approximation will be less than half of the total length. The total length is B minus A. So the error is now B minus A over 2 because this is the midpoint. Now that is after first iteration. Now when we find P2, the second approximation, now the difference between exact and approximation will be less than B minus A by 2 square because this distance is B minus A over 2. That is further divided by taking the midpoint again. So in the first interval stage, we have considered the midpoint. Therefore, the difference between exact and approximation will be less than B minus A over 2. And in the second approximation, Again we are taking the midpoint. Therefore, the difference between exact and approximation, that is the error, will be less than b minus a, the total length, by 2 square, because we are dividing by another 2, as the p2 is the midpoint of the new interval. So like this, if we continue, each time we are dividing by 2, because the midpoint is obtained by taking the length, the total length, and made the length as off by dividing by 2. So after n iterations, the error, that is the difference between approximation and exact, will be b minus a over 2 power n, an absolute. So the length of the interval divided by 2 power n. So if you observe, in the first approximation stage, the error will be less than b minus a over 2, dividing by 1, 2. In the second stage, the error is less than b minus a by 2 square, dividing by another 2 square. Similarly, after third iteration, the error will be less than modulus of b minus a over 2 power 3, and so on. In general, after n iterations, the error will be less than b minus a over 2 power n. Now suppose if this error, if we want the error to be less than epsilon, suppose let us take the error is less than 10 power this epsilon, less than epsilon, then we will get modulus of b minus a over 2n is less than epsilon. From that, if we simplify, 2 power n is greater than modulus of b minus a over epsilon, taking epsilon here, 2 power n to the numerator. So 2 power n is greater than modulus of b minus a over epsilon, taking logarithms to both sides. Natural logarithm, ln 2 power n is greater than ln modulus of b minus a over epsilon. So from logarithm property, this n in the power come before. So you can write it as n log ln 2, n will come before ln. So n ln 2 is greater than ln b minus a over epsilon. So from that you will get n is greater than, dividing this by ln 2, n is greater than ln b minus a over epsilon over ln 2. So this gives the number of iterations n required to get the error less than epsilon. So if we want this much accuracy, then how many iterations are required? Minimum number of iterations is given by this formula. So this formula is useful to find the number of iterations required to get the error less than epsilon in the bisection method. So this formula will use n greater than ln b minus a over epsilon by ln 2, where a and b are the upper and lower limits of the starting interval, and epsilon is the accuracy we need, that means error less than epsilon, that we put here. Then you will get n. Let us see an example. The minimum number of iterations, that is n, required to get an accuracy of epsilon in bisection method. This is the formula as I told. Example, if we need 10 power minus 3 accuracy, if any problem in bisection method, if we need 10 power minus 3 accuracy, that means error is 10 power minus 3. And 10 power minus 3 less than epsilon. In the previous derivation, if you see, error we are taking less than epsilon. We write error is less than epsilon and we are getting this formula. So here error is 10 power minus 3 is less than epsilon. So what is epsilon should be? 10 power minus 2. Because 10 power minus 3 less than epsilon, then epsilon should be 10 power minus 2. So whenever the problem is given, we write error less than epsilon and you choose what is that epsilon. Let us go to another example. find the minimum number of iterations needed to find a root of the equation fx is x square plus 10 cosine x is 0 in the interval -3 -1 accurate to at least within 10 power minus 2 by bisection method. So error we have is 10 power minus 2. So error is less than epsilon. Always we take error is less than epsilon. So 10 power minus 2 is less than epsilon. From that we get epsilon will be 10 power minus 1. So let us put these form values in the formula. N greater than ln b minus a over epsilon by ln2. That is n greater than ln b. B value is minus 1. Minus a. Minus of minus 3. That is plus 3 over epsilon. Epsilon is 10 power minus 1 divided by ln2. That is equal to ln 2 times 10 over ln2. That is equal to 4.32. So n is greater than 4.32 means n is greater than or equal to 5 because n is number of iterations. Iterations will be only positive integer 1, 2, 3 so on. So greater than 4.32 means n should be 5 or more than 5. So the minimum number of iterations required to get an accuracy which is at least within 10 power minus 2 in the bisection method to find a root of this equation is 5 or more. So the minimum number of iterations is n greater than or equal to 5. That is 5 or more than 5. At least 5 iterations you have to do in the bisection method. So this is about the false position method we discussed, which is combination of bisection and secant method, and thereafter we found the minimum number of iterations required to get an accuracy of epsilon in the bisection method. So with this we come to the end of this presentation.